Okay, so before the break, we kind of set up a plan for our next example, a little tip calculator. Wrote out the plan. The big parts there are trivial in a classroom, but you want to practice those, the budget and the timeline. I think we've already ran over our timeline and our budget was based off that. So we'll have to go back and make that adjustment. But we got the whole plan together, all the way down to our pseudocode, the step-by-step algorithm that we need to input in the computer. So for one of the ways we're doing that in this class is with a flowchart interpreter, where we draw a flowchart and the computer can run code based off that flowchart. Low code solutions, things where we use graphics like that, are becoming more and more popular in the actual software development industry, because humans are prone to making typos, but a computer will never make a typo. So there is some big advantages to it. We get a visualization to help us see what's going on, and computers never make typos is one of the biggest ones, because tracking down typos can be very problematic. We'll talk about that some more soon. Let's see. So I'm on my Mac today, so I just remotely access the machines up in the computer lab at school, which have Raptor installed. And we can just do that right from here. So we'll just kind of follow this algorithm. Well, a slight change, one that is often a good idea is, well, just for a check, I just went ahead and ran some stuff. And there's words in our output. So when we ran the next thing, it would show after that. I guess I could go ahead and do that again. Run through these two symbols, just the start and end symbol, but that console is going to get full pretty quick. So a really nice first step to take is calling pre-built functions, and we saw a bunch of that last week. Oh, better save. I'll just go to the desktop. I'll call this tip calculator. So we can use this call box to ask for pre-built code. And a really useful one to start off with is clear console. We want to go ahead and clear what's on there. And to address that typo point I just mentioned, I just typed until it showed up in the little box at the bottom. And here I was able to hit tab and it filled it in. Some of the boxes in Raptor that works on, and some of them it doesn't. We also have that in most of our text editors as well for writing the traditional computer code, where we just start typing the word and the computer will predict the one, try and predict the one we want. And you want to let the computer do the typing as much as possible, because they never make typos. So now our first instruction is to clear all that stuff out of the console and keep some of that mess out of the way. So that's always a good first step. And now we can go right through these. So the first step in our pseudocode up here was to prompt, write some sort of prompt, tell the user we want to know how much the meal cost, and then assign the value they give us to a variable so we can work with it. So that'll be our first step. And in the Raptor flowchart interpreter here, it combines those. It combines those into one thing, which is our input box. So just drag over an input. And prompts are a great place to state this. You've heard me say a number of times now, you don't want to take anything for granted with the machine. Right? Machines are not intelligent. You can't take anything for granted or make any assumptions about the machine being able to figure things out. And usually when you're putting software together, you want to think kind of the same thing about the end user that will be using the software. Leave as little to chance as possible. So when you put together a prompt and say what you want to be very explicit. Explicit and clear, and make sure it's obvious whether you want a number from the user or a word, or be as clear as possible. So let's say enter the cost of your meal, which should should be good. I guess we should include maybe in parentheses, do not include a $sign. I'll go ahead and add that in there for that explicit part, right? If we ask people for a price, out of habit, Americans are going to put the $sign on there. British people are going to put the £sign on there. Most of Europe's going to put the euro symbol on there when we ask for a price, because that means something. There's a nice quote in the chat room there. But we don't want to take any of that for granted, not from the machine, not from our end user, or any of that stuff. So be as explicit as you can. We're going to do math with this. A $sign turns that number into a word, really, right? That's our units. So it's not something we can do math. We can't do math if there's a $sign there. So we want to be as explicit as possible. And with prompts, I always like to end with either a colon or a question mark to make sure it's clear that we are waiting for some input from the user. In Raptor here, it's going to give us a little box, so it's formatted, but still a good thing. So we're going to put up this message. They'll type in a number, and then we need to store that number somewhere where we can work with it. And in the plan, I decided that Bill might be a good name for the place to store that. Same thing for our next steps. Then we want to write a prompt. On the board, I ran out of room, so I just wrote satisfaction, but something about that. How happy were we with the service? Or maybe just how much do you want to tip today? Oops. What percent would you like to tip today? Again, that's a question. So a question mark to indicate that we are waiting for something from the user. But with that explicit point, there's a couple ways we can enter percent, right? Percents are small numbers. Numbers like 0.3. Those show up in the real world all the time. But it's kind of a mouthful. It's hard to say. So what percent really is just an easier way to say that number. If we divide that by 100, our decimal place moves over and then we get a whole number. Or if we multiply by 100, our decimal moves and then that small number becomes something easy to say.
What would the variable be? What would the variable be for a prompt like that said, what percent would you like to tip today?
I was just going to call it tip percent, but we can call the variables are reference names. We make that up.
Or can we just say percent, like in the variable?
Yep, that would work because you're making up that part. So whatever makes the most sense to you.
Yeah, so you're telling the computer what to do. You're telling the Raptor the Raptor system how to work, and
yes, we're feeding in instruction by instruction.
Yep.
And with the prompt here to the user as well as the machine, because there's different ways we could take percent, right? Some people are going to know that if a 15% tip is really 0.15. So they might try to enter the 0.15 like they would if they just pulled a calculator out of their pocket. Or some people are going to put 15 as 15%. So I'm going to go ahead and do it as a whole number. So if we say 15, if we want 15%, we write 15 and not 0.15. So enter what percent would you like to tip today as a whole. Enter the percent as a whole number. That way the user knows exactly what we're looking for. And then, yeah, I always like to end prompts with either a colon or a question mark, depending on which one's appropriate for that situation. And then I was going to call this tip percent, which percent would work fine in this case, Keegan. The main reason I put it as two words is to show that camel case. So whenever we have this, multiple words jammed together, our very first letter is lowercase, then each subsequent word starts with a capital letter. We call that Camel Case. All those capital letters in there are supposed to be like the humps on the back of a camel.
So would tip work? Like if you just put in the word tip, if you did want to put in like percent or something, or would you have to put percent down?
That would work. But then for the next variable, we would need a different name. Because I was going to call the next variable tip.
Okay, so you
That's
know.
the dollar amount after we do the calculation.
Yep. And is this just for the next Raptor assignment we're doing?
Oh, this is just an example on these concepts. Go through everything, make sure to reinforce it one more time.
All right.
Yeah, the assignments that are done outside of the class examples. The class examples are usually stripped down. The assignments typically have something something that you'll have to think harder about than the classroom examples. The classroom examples are stripped down to the base case so you can see the syntax, and you should be able to take that and then think about that next harder step and put together the examples from that. So now we're ready to do our math as per our plan. So we'll set a variable called tip assigned to whatever that tip percent is times the amount on our bill. But I asked the user to give us tip percent as a whole number. So we need to do some adjustment. So now I'm going to come back and kind of wrap that in parentheses. You all remember, let me add some spaces in there so we can see those parentheses. Sorry, I can't make the font here bigger. I can make the other font bigger, but the one in the input box, there's no control over that. Y'all might remember from math class and order operations, if we want something to be done first, things wrapped in parentheses are always done first. So tip percent's a whole number, so we need to divide by 100, which percent. The word per always means divide, and cent is like pennies. So divide by 100 is actually what percent means. It's just in words. So we're going to divide that down so we get that small number, the things that show up in the real world all the time that are just a mouthful when we try to say them, multiply that by the bill. But notice how I didn't do that in order. And that's something you'll find a lot in programming is the computer needs it in a specific order, but that specific order very rarely matches the order we think about it in. So it can actually be a lot more productive to bounce around. You're used to the English language where you work left to right, top to bottom, and the final result needs to be in a certain order as far as left to right, top to bottom. But that might not be the same way we think about it. And it probably won't be because computers process differently than we think. So actually jumping around, moving back and forth can be more productive. Well, we're not working in English, right? This isn't English. So we don't have that left to right, top to bottom restriction. Then we have our tip, and we can just give some sort of output. Print the output. A good tip today. And would be plus what we stored in that variable called tip plus I guess a period to make that a grammatically correct sentence. So try to avoid magic numbers. Even if the answer is obviously just going to be a one number thing, try to wrap it up in a sentence to make sure it's clear what it is. If we had multiple outputs, we could check this box to write them all on the same line or put a line feed afterwards. There's only one line here, so that'll be fine there. But that's the basic process of what we've seen, right? We've seen it a couple times, so sort of reiterating it at this point. Put together a design for what we want to do. Think about the problem that we want to solve, calculating a tip because it involves multiplying by percentages. Bills are a bill at a restaurant's almost never a whole number, right? That's going to be down to the penny. So that's going to have 2 decimal points there, and then a percent has 2 decimal points. So we have to multiply 2 floating point numbers together. So it's usually not a calculation we do in our head, right? So having a calculator do that's kind of easy. That's the problem. So we've put together a design to solve the problem and implement the solution. Now we just check it to make sure it runs. We go through here, enter the cost of the meal without a dollar sign. So $24.68. That seems like a good price. What percent would you like to tip? Maybe it was really good service. So let's say 26%. It's probably a good tip. We can enter, it calculates it. If there's any problems, remember we can always check our watch window and see what values are in there at every step of the way. That looks okay, except we should probably we might want a dollar sign for the output. So come in here.
We always got that dollar sign when we're talking about money, right?
Yeah. Yes, because numbers are meaningless without the units.
Exactly. And plus, you know,
0.1468 could mean anything.
Yeah.
We'll see how to round that to 2 decimal places before long.
And plus, you know,
stuff we need first.
And plus, you know, money is associated with that dollar bill. You know, you gotta get that dollar sign. You know.
Yeah.
Live without it.
So then, yeah, clear the output. We can check again. So let's say 34.56. A bigger meal the next time, and maybe the service was lousy. So let's cut that down to like an 18% tip. And $6.22 for the tip. So it looks like it's working. Then the other thing, there's a requirement in the class for a bug report. You can write that in another document or something. I'll just do it here. And you can also do it in the comments. So if you just right click, why is my right click not working? Well, my right click's not working on the remote access. So that's another thing with remote access. Like I'm on a Mac here, so I don't have a regular mouse that's in the other room. So I'm on the touchpad, which only has the one click button on the Mac. So normally for right click, do the control click and get the right click menus, but that doesn't seem to be working. So you will want to try remote access some because there are slight changes like that. I guess that control click isn't transferring through to the remote computer as a right click. You can also comment up here in the edit. Under edit, there's option to add a comment, and then we can just say stuff. So after you finish, write up a bug report, just letting me know how it went. No big problems. Couple typos. I assume I made typos. Typos happen all the time, right? Forgot dollar sign at first. Yep, there's the progress for making that. It does not have to be fancy. Really, I just want you to reflect back one last time on what you did to solve the problem. So just some notes. And then if there's like common problems that show up in the bug reports, then I'll know that's something that needs addressed in class. But the general format, we've seen the math and stuff. I just wanted to, reflection is an important part of learning, right? Preview, study, then reflect on what you just learned to help reinforce that knowledge. But does anybody have any questions about that? And if you,
yeah, can you run back through the bug report? Like, you know, that's kind of just tricky. You're creating those, you know, header and footer comments.
Oh, yeah, same thing. For the header, you just put it up here. I can't write. You can right click and get that, but under edit is the comment. So stuff like author as date today, whatever the date is.
Program.
Yeah, program summary. Summary, tip
I
calculator.
spelled it with one M.
Yeah, so
Summary with one M.
yeah, just a few notes. Basically, it's like putting your name on an assignment in any of your classes, right? I need to know whose work I'm looking at when I'm grading. Otherwise, I won't know where to put the score in the grade book.
Exactly.
Or comments and things like that. So right click, or if you don't have right click like I don't at this particular moment, there's always more than one option on the GUI. One thing to watch out for though, if you do it here on the school's machines, make sure you save it and send it to yourself somehow. I'll just use the inbox here in Ivy Learn, or submit it directly. That would be a good way to get it. So all the passwords, I think everybody's probably used to that. I think I typed that wrong.
Password managers are my best friend.
Yes. Yeah, there are a whole lot of sites I do not know what my password is. Whenever it asks for it, and if it's still blank, I panic a little. I'm like, I don't know what my password is. I have no idea. How would I know something like that?
Then you have to go through the whole email,
There-
and then like if it's on your computer, email password.
Yeah. Sometimes security things block it though. Oh yeah, Bitwarden's a nice one. The US Treasury website, they have a new thing on theirs. A security issue for entering your password is you have to use theirs. Oh, whoops, not students. I'll send that to myself. Oh, I didn't know Lloyd was still on that list. As example, what is today? 4/4. Put some stuff here and just attach that. Yeah, but the Treasury Department, their newest thing is they have a soft keyboard and the letters aren't always in the same order. So you have to use the soft keyboard to type your password in, which I can see that being very nice and secure. Somebody has to actually be standing there looking at what you're seeing, because I'm sure that's sent encrypted and stuff. But I did lock it down one time because using the touchpad on the laptop, I kept accidentally hitting the wrong keys and locked my account. So there's definitely an annoyance with it at all. But on these, the machines are frozen at the initial login. That way that no matter what happens, if you break stuff in the learning process, all you have to do is reboot the machine, and then it's like the first time you logged into it again. But a trade-off of that is if you save files locally, you're not going to have them if it's the first login. And when you're done, you can just come up here and hit the log out button. Yep, log out. And close all that. Or you can just close your browser, leave manually, and the machine will shut down before too long. It's a useful thing to practice at some point, because the only thing an IT person actually has to be on site for is to plug in loose cables or to push power buttons. That problem we had last Wednesday night, Thursday morning with those computer labs, is there was somebody had to actually go in, somebody that had access, the key card to the secure lab had to actually go in there and push the buttons on the login server. And another one, I don't know what the other one was, but you know, there's only a few things the IT person actually has to be on site for. but remote access is slightly different sometimes, so it's good to practice those. So that's our general process. Think about the problem and design a solution, and that part gets messy. So then you want to clean up that mess and organize it into the sequential list of steps that the computer will need. So clean up the mess. And in a classroom, these two things are trivial, like I said earlier. In a classroom, our budget's always going to be 0 and our timeline is whatever the obvious restrictions on it are. But after you finish the classroom setting and you're out there working for doing stuff for clients and managers, these are the only 2 lines they care about. So you want to get some practice at those. So here, this estimate was 20 minutes. I think it took us probably closer to 40. Yeah, so about 20 minutes before the break and 20 minutes after the break. So it was like 40 minutes. But then this time estimate I put on here, that was based off $5 a minute. So maybe 45. So if it took us 45 minutes instead of 20, that $100 turned into what, 225? So a customer or a manager or whoever would have, that budget and timeline would have been presented to would probably be very displeased with that, right? Or more than double the timeline and budget. So you want to get a little bit of practice with those to get good at estimating those numbers. Okay. Take it, at first, it's just a guess. Take a guess at how long it's going to take you. And then afterwards, look at how long it actually took, so that the next time you'll have a more refined or educated guess, and then that'll get better and better and better. When you're out in the real world, you'll be able to produce those numbers accurately, which will make clients and managers and all sorts of other people happy. So it's definitely worth putting practice into that part. But sort of our general process there. Does anybody have any questions about that before we move on to the next section? Okay, I'm gonna go ahead and erase the board. These have all been up here for a minute now, so that was from before the break, so hopefully they were in your notes if you were taking notes there. Or it's a video, so you can take a screenshot of the video. That works too. So the next thing to go over is actually jumping ahead to module 3 stuff. Time-wise, we're still technically in module 2, but I want to make sure there's a little bit extra time to get started talking about the module 3 stuff, because this is one that there's often questions about. But also I want to make sure we go over it thoroughly because it's not really covered elsewhere. This is the class where it gets covered, and then just kind of go with that. And that's going to be introduction to binary numbers. Getting started into working with binary. So some of y'all may have seen some of this before. We've talked about it a little bit already. When what a computer is actually doing is we have a whole bunch of electronic switches that are either on, open or closed, so on or off. And we usually represent that with 1s and 0s for a couple reasons. One, that it is based off a math thing, which is what we're getting ready to get started into. But also, even when we're not doing math with it, those are really easy symbols to write. A straight line and a circle are 2 of our easiest symbols to draw. So that's what the machine operates on. And it probably seems so confusing. But we started here with just what those symbols represent. And actually, it is something that you already know. You just You just don't know that you know it. So let's take a step back and review something you probably haven't thought about in detail for quite some time. You would have seen this in like second grade, maybe first. So you probably haven't seen it in detail since about second grade. And that's if we have this number, 237. How do we know what this means? How do we know? 'Cause when I write this up here, everybody knows what that represents, right? We put a dollar sign, it could be dollars, right? Pounds over here, could be somebody's weight. Any number of things. Could be 237 pieces of firewood in a stack. Okay? But we all know what that means. And you probably haven't considered in fine detail how you know what that means since about second grade. And we know what this number means because we're humans with 10 fingers. So 10 is a really good number to base all of our stuff off of, right? When we learn to count. 1, 2, 3, 4. We can count up to 10 right on our fingers. So if we need to go bigger than that, that's still a good number to base everything off of. We base it off 10. So the value that this represents is based off 10, and then we organize it into columns based off powers of 10. So what we really have here is 4 columns with powers of 10. First, we have 10 raised to the 0 power, which is a rule from mathematics that you may not have heard recently. So anytime we have 0 as an exponent, that means 1. 0 as exponent means 1. So any number raised to the 0 power is 1. I often like to think of it as, well, we have something. That's why we have a 10 right here, not a 0. But we don't even have one of those 10s. So all we can really say is we have something. So it's our most basic something is just a 1. And then we increase the power of 10. So our next column is represents things 10 to the first power. Then 10 squared, which is 10 times 10, or 100. And 10 cubed, and that pattern just continues. Y'all are familiar with that pattern, so that's probably enough. And then we know what this number, these symbols represent because of where they're at in the columns. So we don't have any 10 cubes. Then we have 2 10 squareds, 3 10 to the first power, and 7 10 to the 0 power, which is 1. And that's where we get that number. So 0, 10 cubes, plus we have 2 10 squareds, plus, in this case, 3 10 to the first power, and 7 things in our 10 to the 0th power column.
Yep.
Sure.
And we're working on that in algebra class actually right now. So, this is perfect.
So yeah, you might have seen that at some point recently. Sometimes it shows up.
And I have had to calculate that, plus it's like, let's just say there's x to the third plus x to the second, minus, x, and then put a number value let's just say +1. And then we have to figure out, the grouping of that. And
Okay, yeah. that's something a little bit differently.
Yeah, but like, you know, of like we're working on this now of this, you know.
Okay, so that's good. So it relates to something. So really, this is something we learned about first or second grade. What these mean. So we don't have any of the 1000s. So 10 squared is 100. So we have two 100s. 10 to the first power is just 10. So we have three 10s. And then 10 to the 0 power is 1. So we have 7 1s. Whoops. 7 times 1. And that's where we get the meaning of that number. So you probably haven't thought about that in quite some time. But the biggest thing that probably wasn't pointed out in like first or second grade when you were learning that is there is nothing special about 10. 10 is just the number of fingers humans use. And then those are symbols we standard symbols to represent it, and we have 10 of them, so we base off 10. I'll put it over here. Base 10 needs 10 symbols. Is in each one of our columns.
Levels of math.
There-
Are there different bases that you use?
Yes.
Okay.
Because there's nothing special about that. I'm going to add a little notation here because we're going to use different bases here in this class. So for our purposes in this class, a little subscript afterwards will represent what base we're in. So 237 in base 10, that's how we know what it means, but that's the system we're familiar with. There's nothing special about 10. We could use another one. So for an example, on the way to where we're going, let's do base 6. So we need so base 10, 10 symbols. So 0 through 9 work pretty well for those symbols. So we want to use those as much as we can because we're talking about numbers here. So we can do math with them and stuff. And I'm going to skip adding columns on that. I assume everybody remembers that, or it'll probably show up somewhere along the way. So if we try a different base 6, we need 6 symbols. We're going to represent numbers, so well, we can just use our first 6 digits. 0 through 5 will work. And then we can represent any number put into columns using the smaller set of symbols the same way. So I'll just do 4 blocks here, only we have a different base. So our smallest column is 6 to the 0 power this time, which again, anything raised to the 0th power is a 1. So still a 1's column, but then our next column, instead of meaning 10, that's going to mean 6 to the first power, or just 6. Then 6 squared, 6 cubed. I think 4 digits will work for this.
I don't like seeing those 6 all over though. Those 666.
Yeah, I just picked an arbitrary one that wouldn't get too big. So let's represent this number, 237, in base 10 as base 6. So we need to know how many 6 cubes we have, which 6 cubed is 36 times 6. What is that? 8, carry 1. 6 times 3, 18, 19. Oh, that's not right. 6 times, oh, carry a 3. And then that gets us 216. We're trying that again. 6 times 6 is 36. So that's 6. And then we carry a 3 to the next column. Get 18 plus 3 is 216. Or the cross thing, the round and adjust. There's multiple ways to do it, however you were learning it. we still we work on it in an organized fashion. Some sort of columns, rows, columns, or maybe the cross thing. And these columns we set up are how we do our math, by simply following patterns. I probably shouldn't have done multiplication first, because all of us might have learned a different way for the multiplication. There's a lot of different ways we can approach that one. Addition and subtraction, we make greater examples for that. But 6 cubed is 216. So do we have any 216s in order to add up to this number? So we're kind of doing the other way from this. So numbers that we add together in order to fill out those spots. Or another way to think of it is we need to figure out how many of these columns have to be filled up to add up to 237. So we start with 237. We have a 6 cubed column, which would be 216. So yeah, I think we'll have one of those. So we have 216. And when we subtract that off, we still have, let's see, 7 minus 6. This is a better example for the columns. 7 minus 6 gives us a 1. And 3 minus 1 gives us a 2. 2 minus 2 is a 0. So we still have 21 left to account for. Our next column would be a 6 squared. And that's 36. 36 would be too big to fit inside of 21, right? So we can't fit any 36s in there. What about 6s?
Yeah, we
6
can.
in the first power.
Yeah, we can fit about like 3 in there. So
Yeah.
6 plus 12, then plus add another 6, you get 18. So you have 3 left over.
Yep. So then we have 3 left over. So we have 3 6s, and now we're over to the ones column, and well, we're at the bottom, so we already know how many ones are left. So 1033 would represent the same value as 237 in base 10. So we can work with stuff the same way. In our addition and subtraction, so I did some subtraction in base 10 there. I should really be writing that little subscript to clearly indicate that. Because our math works the same way. Let's do something in base 6. So 325 plus 141. So there's 2 numbers. I'm gonna put a little subscript 6 on there to show we're in base 6, not base 10. So 325 plus 141. And we're still using all the right symbols. We haven't used anything too big. And we can just add the columns together the same way. So 5 plus 1 is how much? Y'all all know what 5 plus 1 is, right?
6.
Mm-hmm. But we're in base 6. So our first column, or if we look at the symbols, do we have a symbol for 6?
We do not.
So a
Is it like
6
a remainder?
takes 2 columns. Because the number 6 itself, we don't have any 1s, but we have 1 in the 6th column. And this is an interesting little thing. You'll have probably encountered this before. Whatever our base is, the base is always written as 10. Because whatever our base is, whether it's base 6, base 10, base 34, base 17, whatever we want to base our system on, that base itself will always be one of the things in the
Be based around the 1 and the 0, right?
So a 6 is 10.
Yeah.
which takes 2 columns, so we're at a 0 there and carry our 1 over to the next column. Just like we do when we add base 10 numbers on paper. I guess really anymore if we add base 10 numbers, we use a calculator, but when we do it on paper, we use the columns, right? So 5 plus 1 is actually 0, carry a 1. Now we have 1 plus 2 plus 4. Well, that's a 7, right? But how do we write 7 in base 6?
0, carry the 2. I mean 0, carry the 1 again.
Almost.
What was that? Like the volume is
So
low.
if we go ahead and write it out. So to learn it, we're just going to write it out a few times. Machines do this for us. But I am going to ask that you do it at least once by paper just to practice it. Make sure you understand it. So to write a 7, I think we'll have 1 in our 6th column, and we need 1 in the 1's column as well. That makes sense?
Yeah, like an 11. Okay, I'm getting it. Yeah.
Yes, but we want to be careful not to say where it's like 11 when we're in base.
Yeah, it's not, but it's
Because
similar.
11 in base 6 would be 1, 5.
Okay.
11 is a word that has a very specific meaning. 11 is 1 more than the number of fingers humans have.
So it would be.
If we
one
wrote
more
that with a
of the
different
base.
set of symbols, it would appear differently. Multiple ways to write the same thing. So an example I always like to use a couple times as we're talking about programming and computers is humans' propensity to use symbols and patterns. Think of a little kid. Everybody's been around little kids, right? There comes a definite age where that kid, when you ask that kid questions that involve numbers, they're going to try different things. They're going to try the things that you showed them, as well as try some of their own things. Like for little kids, usually around the age of 3 or so, their age is going to be this many. But if you ask them about a quantity, they might say this much. That's the human propensity to represent things symbolically. Is that little kid is very quickly going to figure out that this means the exact same thing to everybody they show it to. But when they say this much, it varies. Along with different people, this much is a different spread of the arms, right? So the human propensity for symbology plays out there. We can use symbols differently to represent different things. And yeah, this column format works the same way. So here, 1 plus 2 plus 4 in base 6 is 1, 1, so it's a 1. We carry a 1 to the next column. 1 plus 3 plus 1 is 5, which 5 is something we can fit in just 1 column in base 6. So does that make sense to everybody? Can I get some confirmations? Head nods, little.
That makes sense.
It made sense. I followed it on paper and starting to get a little bit. It's just rewrite. We're very used to doing everything in base 10, so
Yes.
It's kind of like rhyming it with a different number system in your head.
That's why I went to this intermediate step. So we're used to base 10, but we can carry that on to the one we want now. It's okay if I erase the base 10 side. And does everybody see how that pattern, what our pattern is the columns we lay out, not necessarily the symbols we write in there. It's a pattern that we follow, which is great for machines because that's what machines do. Machines follow patterns. Everybody okay if I erase this side?
Yes.
You can see your notes or take a screenshot or.
Good.
Okay. So the way we work with our numbers, the only thing special about that is the number of fingers we have. We chose a number of symbols that represented the number of fingers we have. We can use any number. We saw here our addition works the same way, subtraction would do the same thing. borrowing's a little bit different. But we'll write that out here in a second. So computers are binary state machines. It's a huge collection of switches that are either on or off. And if this number-based system that we write out by organizing things into columns based off columns built up of powers of the number we're basing things off of, if it works for any system, will it work for 2? Oops, that's not how to write it 2. Will it work for base 2? So there's 2 things we need to make sure work, right? It needs to have a unique representation. We can't represent 2 different numbers the same way. And it needs to work when we do this. When we add and subtract based off columns, make sure that still works. And we end up with something a little bit easier than this, right? When we wanted to know how many, when we did 237 base 10, converted that to base 6, not only did we, when we got to this column, we had to worry about how many there were. If we only have 2 symbols, so we need 2 symbols. We're still considering numbers. So 0 and 1 make good symbols. And since we're going to write a lot of those, I'm going to write my 1s as just the vertical line. Y'all probably noticed I do the fancy ones. I'll tell you where that came from so that hopefully y'all can avoid the same mistake on a very important math test when I was an undergrad. Somewhere in the middle, along the way of doing a bunch of steps, my major was mathematics. So all the math tests I counted as important, but on a very important math test, somewhere in the middle of a problem, the number 301 times natural log of something showed up. And I wrote it like that. I remember 1 is a vertical line and my lowercase l is a vertical line. And y'all probably know it, exactly what happened on the line afterwards. Okay. One of those vertical lines was gone, disappeared on when I copied it to the next line. And then that caused the problem to be missed. So after that, I started writing my 1s like that and my L's like that to avoid that ever happening again. But for binary, we're going to write lots of 1s, so I'm just going to do the vertical line in the class here. I'll go ahead and tell that story in case something for y'all to keep in mind on your math, on your way through school, is you want to be careful when 2 of our different symbols look the same. It's an easy place to make a mistake. So we have 2 symbols.
My Y's used to look the same until I added a curve at the end of my Y's in like 6th grade because of it. Same reason, missed an answer. Couldn't take, like, I was like, okay, from here on out.
Yep, that's the learning process. One of my favorite sentences is we don't learn anything from the stuff we get right. If we just happen to get it right on the first try, you know, that we got it right, we might remember it next time. But when we get it wrong, we will remember it. It makes it memorable. It's forever committed to our minds.
Yeah, plus if you get it right on the first try, then you would not be a true human being if you know.
Yeah, you might or might not understand it. It could have been a fluke or a guess.
Yeah, but humans make mistakes. And
Yeah.
so, you know, it's like we're not perfect. So, you know, the things that we do are not going to be perfect, and we have to try and over again, despite how knowledgeable we are in things. We're not going to succeed at everything. So.
Yes, so don't be afraid to make mistakes. It's a learning opportunity is what it is. Use that word instead of mistake. So we can do this. Let's check
Yeah,
this.
there are no mistakes. Those are not the accidents.
So the same pattern. Our lowest one is 2 to the 0 power. So we can, that's going to be a 1s column. Then 2 to the first, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, 2 to the 6th, and 2 to the 7th, which will be 8 bits. So each one of our ones and zeros is a bit. That's our basic element. Represents a switch. We combined 8 of them into a byte. That was just a chosen size when we made when computers were initially set up. We also have the word word, which we combine bytes into words. But textbooks, that changes. A word is your register size. So if you're on a 32-bit machine, that means your registers hold 32 bits each, which also means that the bus line through the motherboard, where we use parallel communication, multiple wires instead of one, so that a whole bunch of bits transfer at once. The bus line would be 32 bits. So on a 32-bit machine, you would have 32 bits make a word, or 4 bytes make a word. Or on a 64-bit machine, you would have 64 bits make a word, or what is that? 16 bytes to make a word. And then we scale that up into pages, which has to do with some other size issues and stuff. So for class here, we probably aren't going to write more than 8 bits because it takes a lot to write binary, which is one of the big points we'll get to very, very shortly. But if we wanted to write 237, well, you might not know what all these numbers are. These are easy to find because we just double it. So we know we have a ones column, so we double that to get a 2. For a 16, twice as much as that's 32. Double that to get a 64, and then we have a 128. So if we use the same number, I'll come over here to where we're subtracting it. Well, this time we need to subtract off the base 2 numbers. So our first column, when we're doing it this way, it's good to start with the biggest column, is 128. Can we fit any 128s in 237?
Yeah, at least one.
And with binary, it's a yes or no thing. We either have that column or we don't, because the only thing we can put there is a 1 or a 0.
Yep.
So that even makes it a step easier because we either have it or
We can't use the 128 twice, but we can use it once.
yes. So if we subtract 128, oh yeah, so doing subtraction in column 7 minus 8, well, 8's bigger than 7, so we can't really subtract, but we can borrow from the next column, which I'm over in base 10 again over here. So the next column is 10 bigger, so then this becomes 10 plus what was already there. So 10 plus that 7, so now we have 17. We can do 17 minus 8. We already borrowed one from these. Y'all remember doing all that, the borrowing and carrying? That's the important thing. We need to make sure our column system works with 2s. 2 minus 2 is 0. 2 minus 1 is 1. So we already filled our first column, so we're over to the next one. Can we fit a 64 in 109? And we don't have to worry about how many of them, because we can only have one of them.
We can fit in like once.
So yes. So this becomes a yes or no question. What is that?
Okay.
Same thing. 9 minus 4 is 5.
Yeah.
0 minus 6 is too big, so we have to borrow this one and do 10 plus 0. Then we can do 10 minus 6 to get a 4. And we don't have anything left in that column. So just a 0 there. So all that carrying and borrowing stuff we haven't seen for a while.
We can also fit 32 within 45 I meant.
Yep.
And you will get 13. And then the next one is actually 0. You can't do that.
Exactly.
But you can do it with 8.
Yep. Somebody else want to answer a couple of these?
Okay, sorry.
All right. I just want to make sure everybody gets it because this is a very important thing. And
Yeah.
This
I
is
can
kind of the
I
only
know
class that
math.
covers it.
I know my math pretty well. It's just
Yeah, so
don't
like
get
you said,
excited.
we can fit an 8 there, which leaves us a 5. Does somebody else want to answer? Can we fit a 4? Is that a yes or no? Do we have a 4?
Yeah.
I think I heard a yes.
Yeah. Sorry. It was halfway. I was between muting myself now.
Which leaves us 1. So well, we're not going to be able to fit any 2s. Right?
No, you will not.
No 2s, and then yes for a 1, and that gets our number. So then that's what 237 looks like in base 2. So numerically, that's how we represent our numbers. And see how it's something that you already knew. People think binary looks so confusing, but it's actually simpler than the numbers we know, because we don't even have to worry about how many we have in that column. It's just a yes or no question for each column. And then the same way we add up the values by just the column.
That's why when I was doing the labs for test out, the limit of the number was 255.
Yes.
For binary code, anything over that number, and I even when you play even sports games, for example, I play Madden, for example, and it won't go past 255.
Yes, because that's the limit. So I'm not going to write it here on the board, so the people that didn't talking weren't
Sorry.
giving any answer. The answers there. Write down 255 in base 10, and then convert that to binary just to make sure you can understand the process and see what number that gives you. There's a pattern to recognize there. We can also add and subtract. We should be able to if that's a valid number. So let's take a look at that. And that'll finish up our first discussion on this today. What time is it? Oh yeah, right on that. So I'm just going to do 4 bits because that's easier to write and that's enough to see the patterns, right? We don't need to write 64. We don't need to try to add 2 64-bit numbers. 4 bits will let us see the pattern. So let's add 1101 and 0110. What are these numbers? So if we convert this to base 10, we just need to add up those columns. So we have a 4-bit number, so we only have this much. So our first one's 2 cubed. So we have a 2 cubed plus a 2 squared. We don't have any 2 to the first, and then a 2 to the 0. So 2 cubed is 8, 2 squared is 4, and 2 to the 0 power is 1. So 8 plus 4 plus 1 would be a 13. And same thing down here. We don't have any 8s. We have a 4. Then we have a 2. We don't have any 1s. So 4 plus 2 would give us a 6. So if we add those, we should get a 19. And then we do straight down our columns like we did, like we learned way back in elementary school. So 1 plus 0 is how much? And that's not a trick question. So what do we get when we take 1 plus 0?
1 plus 0, you get 1.
0.
So the next one, 0 plus 1. Well, that's the same thing. That gives us a 1. Well, what's 1 plus 1?
2, but you can't have 2 in a binary code system. So a 1 and a 1, that would probably 0, right?
I think so. I think you said an extra number there. But 1 plus 1 is 2, which is our base, and our base is always written 1, 0.
Yeah, exactly. So it's just the 2
So
only
that's
numbers.
0, and then we carry a 1 to the next column. And once again, we have 1 plus 1 is 2 or 1 0. So now if we check this, we have 5 bits. 1, 2, 3, 4, 5. So that's a 2 to the 4th column.
Yep.
So it looks like we have a 16. We don't have any 8s. We don't have any 4s. So we have a 2 and a 1. So 16 plus 3 would give us a 19. So it looks like the adding checked out. These numbers will work for subtracting too. So let's subtract those. 1, 1, 0, 1, 0, 1, 1, 0, and we're going to subtract it. So what's 1 minus 0? Again, not a trick question.
1.
0 minus 1's, that's what we had when we were subtracting over here, right? Only we have bigger numbers. We have our decimals, but the number on top is smaller than the number on bottom. So we have to borrow from the next column. And when we borrow, our next column's a power of 2 bigger. Whoops, that's supposed to be binary. So we borrow 2 or 1 0. So what's 2 minus 1? Again, kind of easy, right? Hopefully this is seeming very easy. When we borrowed, that left us a 0. So once again, 0 minus 1, we need to borrow from the next column to do that. We borrow a 2, which is written 1 0. And then 2 minus 1 is just 1. And then 0 minus 0 is easy. So what number did we get there? 3 bits, so 2 squared, so 4 plus 2 plus 1, 7. I see that in the chat room. So 13 minus 6 should be a 7. So it looks like everything checked out for us. We're able to uniquely represent all of our numbers by adding up different columns of 2, and it still works with our doing the math in columns for carrying and borrowing. So that's what base 2 is. That's binary code. That's the fundamental part of binary code. You probably noticed that when we do this, we did that, right? That was a whole lot of thinking internally based off what we already know. So the machine can't quite do this. We still have some more to go before we can get to what the machine does. But that's our basic base 2 representation. And see how it's something you already know? You just didn't know you knew it. It probably looks so confusing when you'd see all those. It's the exact same thing you know from working with numbers. And actually it's a step easier because we don't have to worry about how many we have in each column. We have a yes or no question in each column. So there's still some more stuff we need to address, some more representations and stuff, but I wanted to get about that far and get started into binary, which might take a little bit of practice, but the practice there should be easy, right? Make up a number and then convert it. Just write down some random number and then convert that to binary, or write down a binary number and convert it back to a decimal number. Does anybody have any questions about that?
No question, just a statement. These are the exact things that, like, the different ways to express base 10s that we were talking, that I mentioned. I was like, oh, how do you can use that to do different things, and we just immediately went into the different things that you actually do with it. So immediately saw the application. Thank you.
Yes, so we're going to take it a little bit further, but this is the basic binary representation. Well, then our symbols are really easy. I can say that right now because now we have numbers. So we can say things like a capital A is the number 65. A capital B is the number 66. Capital C is the number 67. I think you see where that's going. And we do all of our symbols that we use that way. And that's what ASCII code is. But then we ran out of symbols, so we extended that. So ASCII code is just the first 255 bits. 255 symbols was 256 symbols wasn't enough. So we extended that to 16 bits, and that's what Unicode is. We can say, okay, this symbol is represented by this number.
Official name for the binary symbols represented by characters?
Yes, ASCII is American Standard Code for Information Interchange.
Okay.
I'm not positive about the last I, but American Standard Code Information. Coded information. So it covered American symbols, but well, there's the Chinese alphabet, Sri Lanka, their alphabet looks like you're drawing flowers on the page. And all over the world, there's different alphabets, right? So we needed more than just the American. Also, this is not a new thing. Egyptians used base, when I did my history of math class, Egyptians used base 2 to do their math. They extended it a little bit, but they added and subtracted and multiplied based off power, basing off powers of 2 because they're easy to work with. It becomes a yes or no question. We don't have that external thought of like how many. It's just yes or no. Hopefully that makes sense. I wanted to get that far today, just the basic representation, because on Wednesday we'll get into making this more complicated so that we can actually set up a machine to do it. Does anybody have any questions? Okay, so it looks like we have about an hour and 10 minutes left. As always, until our scheduled time at 4:50, I will be sitting right here by the computer, ready to jump back on a Zoom call if you have any questions. Otherwise, that was it for today. Remember, text messages and Ivy Learn messages make noise on my phone. Let me know if you have questions, and otherwise I will see you all on Wednesday and we'll pick up from here then.
I'm gonna convert some pop culture references to binary. Like
It's a good start to practice, isn't it?
One Futurama for sure.
Oh,
I'm
yeah.
gonna try and do that for my homework.
Nice. I'll see you Wednesday.
Later.